Okay. Okay. Welcome to the CMTC seminar today. It is my great pleasure to introduce Andrei Bernevig from Princeton as the seminar speaker. So Andrei did his PhD at Stanford and then went to Princeton as a postdoc before joining the faculty at Princeton. And Andrei has done numerous seminal works on topological physics of matter, especially band topology, and also on quantum dynamics. And today he will talk about the mapping between TBG and heavy fermions. Andrei, please.
Thank you. Thank you so much for inviting me. And sorry I couldn't be there in person. It was one of the only times I could visit some family. Most of the work that I'm going to be talking about was done at the beginning. Talking about at the beginning was done in collaboration with Gilles Song, who's now at Peking University, and then hopefully I will get to work done by Jonah, Aaron, Fang later. I want to thank some of the senior collaborators, also more senior collaborators, which are in the second row. So of course, I'm giving a talk at a place that's very familiar with twisted bilayer graphing. So I'm going to give a very short introduction to the subject and then delve right into the subject. So what we're going to be talking about is the physics of the correlated states at the beginning of two twisted layers of graphene that create a moire pattern. And this moire pattern, which you can see here at a larger vector than the original lattice, basically has two regions, the AA region and the AB region, which are these two regions in the larger moire unit cell. And the band structure that is created comes from one of these models, the most famous one being the Bissett-McDonald model, where at an angle that's 1.05 degrees, you get two very flat bands and a small gap to the next called passive bands, or what we'll call passive bands, at the gamma point in the Moire-Briand zone. These two bands per valley, which I'll talk about a little bit later, per spin, basically can give you can let you put 8 electrons per unit cell in them, so 2 times spin times valley. And you can go from a filling by gate doping, you can go from a filling of -4 to 4, filling up these bands and going in between the single particle gap here and the single particle gap here. Now, by band theory, going through these fillings, you would get to have a metal. However, what is seen experimentally is this series of insulators at integer filling, you can see them here, and pierced by some superconductors. Now, there's many different experimental samples sometimes give you different answers, but the sort of overarching idea is that there are insulators and integer fillings. Different samples give you different integer fillings. There's some samples which see an insulator even at 0 filling, not all of them, actually not most of them, at charge neutrality. But this would kind of be the cartoon picture of it, and there's superconductivity in between them. Now, there are many other experiments that give you many other states of matter around these insulators and superconductors, such as strange metal, Chern insulators. Even some of these correlated insulators are thought to be actual Chern insulators, etc. And there's Pomeranchuk effect at some higher temperatures here, and there's strange metal some everywhere in these regions, etc. And there's also Dirac behavior, Dirac electron behavior noticed. There's quantum dot-like behavior noticed. It's a wealth of many body phases of matter. Now, in this wealth of experiments, I want to point out a contradiction. And the contradiction is that there's experiments which clearly see or suggest the existence of local moments, and there's experiments which clearly see or suggest the existence of delocalized electrons. One of the simplest experiments that sees the existence of local moments are STM experiments, and there's a series of them these STM experiments can basically see Coulomb blockade data that basically tells you that you've got a huge repulsion, very localized electrons on the AA sublattice of the Moiré lattice. This is the AA, and in fact, one of the early fittings of such experiments done by Biao-Liang was by considering just a Hubbard-U quantum dot type model, and you could fit the experimental data pretty well, even with just the Hubbard-U, the STM data, even just a Hubbard-U quantum dot model. And then there's Pomeranchuk effect experiments, large entropy in the ordered phase, which appears under a magnetic field, which basically suggests the existence of loosely coupled local moments, and these are the references. But of course, there's also many experiments which suggest the existence of metallicity and superconductivity, or Landau fans, etc. So these suggest the existence of delocalized electrons. So in this contradictory picture, we have both local moments and localized electrons, as well as delocalized electrons. So if we were
I have a question, Andrei, but
yes.
Are both things ever seen in the same sample? Maybe there is no contradiction. Maybe different samples have different physics. I mean, that's certainly allowed if there is disorder, and so I'm saying, generically, right? That's allowed.
That's true. Yeah. So now you can. So that's a very good point. So now you can actually see. So the metallicity and superconductivity at the beginning, as you know, they were seen in transport experiments, but now you can see superconductivity in STM also.
Oh, I see. Oh, I didn't realize.
So I think Stefan and Ali and now Eva, but I think these two papers, Stefan Asperger, were seeing it, and they were seeing superconducting gaps open in the same sample, where if you go to AA and at higher temperature, because these are large energy scales, actually, these are 40 electron volts, 3040, the Hubbard-U here, supposedly, well, from fitting comes out to 3040. So they can, if you lower the temperature, there are now samples where you can see both this and superconductivity in the same sample.
I didn't know that. That's very interesting. Okay. All right.
Yeah, so I think it's very recent, the papers, I think 2-month-old at the most, but Natch Pergy, and then a week after those.
Thank you. Continue. Okay.
Thank you.
I've answered my question.
Very good. Yeah. So indeed, so you do so this is important. You do have these localized, delocalized, contradictory picture even in the same sample. And if you were to take this at face value, then you would build a phenomenological model. Now, what we're not going to build a phenomenological model. Everything is actually derived from analytics. But if you were to take this and try to build a phenomenological model, you would want to build a model consisting of both local moments and itinerant electrons. And local moments basically would be responsible for the flatness or the localization of the band. And the itinerant electrons, which could possibly come, for example, from a delocalized wave function, which could possibly come from topology, for example, would be responsible for the delocalized electrons. But we know basically what a model of local moments and itinerant electrons is. That's a heavy fermion physics model. And the main part of the talk is going to show you that you don't need to do a phenomenological model. You can actually derive an exact mapping between the magic angle twisted bilayer graphing and a heavy fermion model. And I would argue that even on more general grounds, there are mappings between these type of flat band models and heavy fermion models. And these heavy fermion models are actually a little bit special in the sense they're topological heavy fermion model, in the sense that the conduction electrons actually form a topological semi-metal. All the parameters in this model in the original paper were calculated in a first principle way by doing numerics. Now we can actually compute them analytically. I'll show some results, unpublished results. And in terms of the many-body correlated insulating states, this model actually explains some results in strong coupling, some numerical results that were seen in strong coupling that couldn't have been explained before. And I want to argue that it's a natural way of understanding the correlated states, because you will see that the correlated states just come out of the localized fermions polarizing under Hubbard-U, and then influencing the conduction fermions. And I want to argue that there's some insight into Pomeranchuk superconductivity and other physics here that's not fully determined, of course, but that could be work in progress. I'm going to start with the construction of the model. And to start with the construction of the model, we have to start with the symmetries of the twisted bilayer graphene. The symmetries of the twisted bilayer graphene are the followings. There's a symmetry, there's a magnetic space group. And the reason why there's a magnetic space group at play is the following. If you take 2 layers of graphene and twist them by a small angle, then the physics will come from the lower Dirac node at the K point of the lower sheet and the Dirac node at the K point of the upper sheet, hybridizing, okay? And also the same from the K prime point. But if the angle is very small, then it takes you a lot of tilings to actually scatter from one K point to another K point of the original graphene lattice by tiling this small Moiré-Briand zone. And this gives rise to an exponentially suppressed hopping between what we now call valleys. And K is one valley, K prime is another valley. And this leads to a valley symmetry where you can basically consider in single particle the model in a single valley. And this model in a single valley now has a magnetic symmetry group. Why? Because the original graphene time reversal moved you to a different valley. So if I'm valley filtered, I don't have time reversal because that switches the valleys, but then C2Z moves you back to the same valley. So the symmetry group contains this C2Z times time reversal symmetry, and it contains value 1, etc. Now, what you can do is, by knowing these symmetries, you can immediately prove the following thing. You can look at the flat bands, which come out of, taking these 2 Dirac cones of the lower and upper layer at the K point, introducing hybridization between them, and resolving the band structure. You can look at the flat bands and immediately find the representations of the flat bands at high symmetry points. And these are fixed by symmetry, it turns out. There's no other way. If you respect all the symmetries, there's no other way to have these representations. You can change M1 to M2, G1 to G2, but you'll still have these representations of the bands at the high symmetry points. Now, these representations of the bands at the high symmetry points, they're just some labels. You can check them out in the crystallographic book. But the moral of the story, then the important thing here is that if you try to ask the following question, are these representations the representations of any localized orbitals? The answer is no. And the way you see that is by realizing that you can go to the Bilbao crystallographic server, which is a website where you can now type in the symmetry group and find all the representations at high symmetry points of bands that come from localized orbitals. And for this symmetry group, these are the representations of localized orbitals at all high symmetry points in the Briand zone. So for example, this is a PZ orbital at the A position, this is a PZ orbital at the C Wyckoff position, etc. And you can see that there's no way you can just, you can trust me, or it's a very simple linear algebra calculation. There's no way to make these representations of the bands as sums of representations of the atomic limits. Hence, it must be that these bands cannot be written down as localized orbitals, these 2 flat bands. Hence, it must be that these bands are topological. And in fact, there is an obstruction to 2-band symmetric and local lattice models on this as a representation of these 2 bands in terms of local lattice models that are 2-band and that respect the full symmetry. And these bands are topological. Now, to understand what type of topology...
May I ask you a quick question, because I like following everything. These symmetries that you explained very clearly are all in the Bistris and McDonald model. What I'm asking is, how dependent is your group theory analysis on the model of the band structure? That's what I'm really asking. Yeah, so
so basically, okay, so that's a very important question. And I think there's a very... there's a clear answer and then there's a less clear answer. The model that comes out of taking 2 Dirac cones, which are the K of the lower layer and K of the upper layer, the Dirac cone has particle hole symmetry. Actually, if you sit at the linearized, right? If you sit at if you're at the linearized approximation and maintain particle hole, which actually in these Bistris and McDonald models is maintained to better than 0.3%. So neglecting particle, accepting particle hole is the same you introduce the same error as neglecting spin orbit coupling. So let's, if we assume particle Hall, then these are the representations. If I have two bands, no matter whether they're flat or not, around charge neutrality, then these have to be the representations at any angle, at any. So as long as I can have the angle small enough to neglect the coupling between valley K and valley K prime, then these bands have to be topological at any angle. So that's a very good, that's a very important point, and thank you for asking it. It's these bands, as long as you keep particle Hall symmetry and the symmetries of two layers of graphene.
Yeah, you answered the question. This is what I wanted to hear.
Irrespective of the model, yeah. So irrespective of the model, you can prove that these guys have to have these representations and have to be topological. Now, of course, you know, the same representations come into the well, the time reverse representations, but they're saying into the other valley. And if you take the two valleys together, then they're trivial.
Yeah, okay, this is a very important one. I'm thanks that you explained it. So it's actually quite general. All you need is particle Hall symmetry, and
all you need is particle Hall symmetry and these and the valley. The fact that they need to be the small valley in order for the two valleys not to communicate. If the two valleys to communicate, you put these two topological together, and it becomes
the U1 symmetry you're talking about, which we always assume anyway. Right?
Exactly. So this is a very important point. This is it's actually not, so it can be, you know, calculated immediately here, but it can be shown. It can be shown with particle Hall symmetry.
Yeah, am I correct in saying as long as there is particle Hall symmetry and U1 valley symmetry, this, what you just told us, is a general result?
That's right. And because particle Hall symmetry anti-commutes, you see, the reason why there's a G1 representation here in the G2 is particle Hall anti-commutes with C2x, with a spatial symmetry. So it flips these, and that's why these are fixed to be M1 and M2, which are the two representations of C2x. And if you do this, you immediately see that, because we have all the atomic limits, there's no way to write this down as a sum of atomic limits. So yeah, so just as you said, if you keep particle Hall and valley, and of course the spatial C2ZT, etc., then, excuse me, then it's there in irrespective of the model, where I use Bistus and McDonald or some other longer range, yeah, very good. Okay, so we know that these are topological, as we just explained in any such model. So now the problem is asking what the topology is. And I'm not going to get you through the history of it, but at the beginning there was history of saying that this topology is fragile. It turns out it's actually not fragile; it's stable. And it turns out it's a very interesting type of stability. Here, these two bands here, very low here, are the flat bands of the Bistus and McDonald. This is at a different angle, okay, where bands become more bunched together. But now we can look at 10 bands around charge neutrality, and we can plot their Vanya centers, or as it's also known, their Wilson loop. The Berry phase in one direction is a function of momentum in the other direction, and you can see that it winds across the Briand zone. By winding across the Briand zone, this means that the Vanya center cannot be localized. If it was localized, you'd have no winding, for example. It would stay, as I move the momentum, it would stay sort of fixed. It could wind, it could move a little bit, but stay. But this winding means that there's no way to basically make the Vanya center localized. So these bands, if I take 10 bands or 20 bands, are topological. So these continuum models are very interesting in the sense that no matter what the bandwidth I go to, what's the bandwidth that I go to, or how many bands I take, they will always stay topological as long as I keep particle Hall symmetry and actually C2Z times T symmetry and valley symmetry. So these models are always topological. Now, of course, you can say, well, how can that be? I know that when I add all the orbitals in the problem, then the model has to be trivial, because all the orbitals, if I add them all, the orbitals are localized in the end. And this is true, but this is a continuum model. So what happens is that as I go to large bandwidth, the other value will come in a realistic model where I take the graphene, say I would do atomistic calculations, the other value would come in, and that's how the topology would get spoiled, by bringing the other value in. But this is a continuum model. It doesn't have a bandwidth. And if I take the graphene bandwidth, the original graphene bandwidth to be infinity, notice the scales here are much smaller than the 6 electron volts or whatever of the original graphene. And in this case, you can see that this model is always topological. So there's another way to understand the topology. When you have particle hole symmetry n C2Z times t, the topology, this topology, which is strong, no matter how many bands you take the topological, is equivalent to the existence of 4n plus 2 Dirac points at 0 energy. And this 2 is fundamental. This, I can take to be n to be 0. So it's equivalent to the existence of 2 Dirac points at 0 energy. And this is basically a symmetry anomaly that's reminiscent to the Foucault anomaly, except for Foucault anomaly, it's on the surface of a topological insulator, and it's got 1 Dirac cone. This is a anomaly that's not at the surface of anything. It's got 2 Dirac cones at 0 energy. But it still cannot be realized in a lattice model, the same way that a single Dirac cone cannot be realized in a lattice model with just time reversal. Same story as Foucault. This just has different symmetries. So now you can show that you cannot realize 4n plus 2 Dirac nodes in a lattice model with particle hole and C2Z times t. So this is a symmetry anomaly that forbids the symmetric and short-range lattice models with any finite number of bands. And there are lattice models with finite number of bands in the literature, initially by Kang and Buffet, Koshino, etc. But in these models, the symmetries are basically implemented non-locally. Okay, so time reversal, for example, is implemented non-locally in this. So there's no way to implement time reversal and all the symmetries faithfully locally and have a lattice model, or there's 10-band models such as the model of Poe, but in this band model, particle hole is broken. It's not even non-local, it's broken. Now, as an interesting consequence of this symmetry, and something that we actually were working on, but got scooped by you guys, is that superconductivity is very interesting, and it leads to basically gapless superconductivity if certain conditions are satisfied in twisted bilayer graphene, and it also leads to Majorana points, Majorana fermions, 0 modes at half filling in proximity induced superconductivity. So now, having this information that the 2 bands here are topological, we want to get to the construction of a heavy fermion model. Now, first of all, we want to get to the construction of the states that make the this pattern in STM. This is the AA sublattice, the A of the Moire lattice. So this sits here, as you can see them, Moire, and we want to ask whether we can make something that looks localized, like this guy. This guy looks pretty localized, it's charge energy, that looks localized, that sits on the A sublattice. Now we know that there's no way to do this with just these 2 bands because they're topological. But if we look close to these 2 bands, if we look in this energy range, for example, which is still accessible by Hubbard-Dew, etc. So if we look in this energy range, we see that the next bands have a gamma 3 representation here. And we see that if we borrow the gamma 3 representation, instead of having at the gamma point, gamma 1, gamma 2, then we look again in the Bilbao crystallographic server, and we see that a band that has a gamma 3 representation at the gamma point, a K2, K3 at the K point, okay, and an M1, M2 at the M point, can now be written down as atomic orbitals. And it can be written down as PX, PY atomic orbitals exactly at the AA Wickow position. So exactly where the STM wants it. So this makes you wonder about building Vanya states at the AA position. So what we do is we introduce 2 trial Gaussian type Vanya states, which are PX plus IPY orbitals, which sit at the AA position, and compute their overlap, okay, with the 6 lowest Bistritzer-McDonald bands, not per value per spin, not just these two flat bands, but also, as I said, these part of these next bands in order to have the correct representation gamma 3 at the gamma point. And what you find is that if you now plug these overlaps into the Vanya 90 program to build maximally localized Vanya states, you find that you can build out of these Bissester-McDonald bands extremely localized Vanya states out of these 6 bands with a spread which is 0.2 the Moiré lattice, and hence the hopping between these two Vanya states is 0.1 milli-electron volts. So these Vanya states are basically localized electrons. Now, at the beginning, what we did when we did this numerically. Now we have unpublished calculations where we can actually get the spread analytically from the parameters of the Bissester-McDonald model. For people that are familiar with the Bissester-McDonald model, these are parameters of the Bissester-McDonald model, and this is now the spread of the Vanya state, which has a very nice analytic form in terms of parameters of the Bissester-McDonald model. I won't go into that, but what I will go into is that now you can ask, having built these Vanya states, you can ask how much of the flat band. Yes.
Andrei, could I disturb you again? I'm really trying to understand everything.
Yes.
I have a lot of stuff here.
Yes. No, please.
This highly localized one-year state that you said you originally got it numerically, but now you have some analytical argument. I totally believe it. But my question is, how stable is it, including even more bands? After all, the system has more bands, right? So
yeah,
does it
very stable
perturbatively at least?
It's very stable. At this angle is very stable because, okay. Yeah, that's a very good question. So this angle is very stable because you see, so I'll explain. I'll explain right now. I'll explain right now why. But you see, like basically, so the dots here in this picture are the overlap of these Vanya states with actually the Bissester-McDonald bands. Now, away from k equals 0, at k equals 0, we know at the gamma point, we know they have to have 0 overlap because actually the Bissester-McDonald bands have different representations than the Vanya states. The Vanya states have gamma 3. That's why we used the next band, right? So that's why we used here at the gamma point.
So you need 6 bands, right? Yeah, I got
that. But away from it, they're very, very good. Now, away from it, you can also see that the Bissester-McDonald bands go up in energy. And there's all these other bands here, but they're basically, they'll come with an energy denominator, and these will not. So at the magic angle, including extra bands doesn't make much change in this. That's very good. Yeah. So, and I would argue that basically this is actually what I was going to argue at the end, but maybe I talk about it now, that this is kind of a, this model, basically this heavy fermion model. Once you have this large separation here, then it's likely that all these flat bands will come from a heavy fermion model, and all the Berry or topology will come from this small gap, which is basically where some inversions can come in. But the topology will come from where there's small gaps, and everything else around here is going to be heavy fermions. But right, so this is very important. So introducing extra bands at the magic angle doesn't make much difference because they're far away. So then you can, thank you. So that's very important. And then what you can ask is also how much of these Bissester-McDonald bands are contributed by the Vanya states, by these localized Vanya states. And you find out that a staggering 96% of them is contributed by the Vanya states, by these localized Vanya states. So 96% of these Bissester-McDonald bands, if you take this overlap, is just these localized Vanya states, whose Hamiltonian is 0 because we don't have any hopping basically between these two Vanya states because they're so localized. And now we argue that basically this correlation physics of flat bands must mainly come from these Vanya functions. And I will show this by actually computing the Coulomb interaction. But we know.
Andrei, can I ask a question?
Yes.
Yeah. So I'm curious, how does this depend on the angle? So certainly magic angle is important, but I'm just curious, is there a very simple way to understand why it must be magic angle?
So that's also a very good question. So basically, so you can build Vanya states by borrowing. So by borrowing this, by taking these representations, okay, you have to take this gamma 3 also, because otherwise you couldn't build localized Vanya states. But by taking these 6 bands, I can always build these Vanya states. Now the question is, how localized will they be? And of course, if you go away from the magic angle where you start getting dispersions here, okay, then this spread is going to increase, and then this hopping is going to increase. So So if you go away from the magic angle, like for example at 1.5 degrees, where you have some dispersion, okay, you have quite large dispersion actually of these flat bands. And this is related to what Shankar was saying. Then these bands become, start talking, and the spread of the Vanya states starts getting larger. Their interactions, their hopping starts getting larger, and their Hubbard U, which I'll compute, starts getting smaller. So then, you can still build a heavy fermion model, but it's not that heavy, and it's not, it's not that useful, because you don't have, right now we have a very good separation of scales, in the sense that you have these very localized fermions, which will have a large Hubbard U.
But
does that make sense?
It seems to me, based on what I understood, is that it's not like a set of measures zero. It's not like you have to sit exactly at the magic angle. You can go a little bit out, and the model becomes progressively worse. But that's
exactly.
That's true in all of condensed matter physics, right? I mean,
exactly. Yeah, you don't have. Yeah, you don't have. So what we're doing right now is
the point that you go away and it just goes away. No, it's a quantitative thing. The
sure, exactly. So what we're doing right now is exactly this: is scanning the angle parameter and seeing exactly where it is, where it's a quantitative thing. So as Shankar said, like this, this gets worse progressively. At the magic angle is very good. It's very sharp. If you go away from magic angle, it's going to become worse and worse. And then you can quantify sort of, I'll show you basically where, so you're going to have, I haven't told you about where the C electrons are. I've only told you where the Vanya states are, where the F electrons, so these we'll call F electrons because they're the localized states. I told you where these F are. So these F will hybridize with the C electron. When that hybridization becomes larger than the Hubbard U, I would say that this model is physically not correct anymore. But in close to the magic angle, 10% plus or minus, it's still, the Hubbard U is still larger than the hybridization, and this heavy fermion picture is good, very good. I like these. I like your guys' seminar. It's much better than all the other seminars I've been to. There's questions.
Well, you know why? That's because this is a pure theory seminar. This is.
Oh, I see.
We got rid of all those general talks. My thing is that we should have the style, but it should be a technical talk without any BS.
Yeah. No, this is much better.
Yeah, we are theorists, right? But I'm actually enjoying it a great deal. I'm learning a lot. Thank you.
Yeah, no, I'm learning a lot too by having all these questions. So it's great. Yeah. Okay. So so I've told you where 96% of the states of the Bicester-McDonald bands come from. They come from the Vanya, from these localized F electrons. Very localized.
Let me ask you something. Are you going to show us numbers later on as you slightly go away from flat band? What does that number become? It goes down, I presume, but as you go away from the magic angle.
Yeah, it goes down. So I can tell you that at around 1.15, it's 80.
Still 80 at 1.15. So that's the answer to Young's question.
82%, something like that. Yeah.
So there is a quantitative answer to Young's question then. Okay.
Exactly. Yeah. We're doing now the full mapping versus angle, but the number that I do know is at 1.15 because that was the one I computed, is 82%. Very good. Thanks. Okay, so now, so at the magic angle, 4% of the states are not given by this heavy fermion localized states. And this is clear why not, because at the gamma point, the Bicester-McDonald bands have different representations than the heavy fermion states. And these different representations make the band topological, and obviously give you zero overlap with the heavy fermion states. So we need to model the remaining 4% of the states, which are the delocalized states. And these delocalized states, now you can model them immediately by, you can calculate them, not model them, by taking the projector into these 6 bands, which is what you used to build the Vanya states. And from the projector into these 6 bands, which I'm going to call 1 here, this is the projector into these 6 bands, you remove the projector into the heavy fermion states, which you've already built. You've already built your heavy fermion states. So you remove the projector into the heavy fermion states. Now, these 6 bands had a gamma 3 plus a gamma 3 plus a gamma 1 plus a gamma 2 representation. Okay, the heavy fermion states at the gamma point had a gamma 3 representation. Hence, the leftover states at the gamma point, 1 minus PF, have a gamma 3 plus a gamma 1 plus a gamma 2 representation. Okay. And hence, they're formed out of a two-dimensional representation. Gamma 3 is two-dimensional. This is gamma 3. Okay. And a gamma 1 and a gamma 2. And you can see that the Hamiltonian is a 4x4 Hamiltonian of just these conduction, these extra states that are not given by the heavy fermion. And there is a very simple form of these states. There's nothing in the gamma 3 up to first order, up to second order. And then there's a linear coupling between the gamma 3 and gamma 1 or gamma 2 representation. And the reason for that is that these are just angular momentum 0 or 1 under C3. Okay, so then they have a linear coupling, and there's a splitting of the gamma 1, gamma 2 representations, which is M. Okay, so now you can backtrack these, you can calculate these from first principles from the Bicester-McDonald model, and you find these values. M is 3.7 milli-electron volts, and this V star is minus 4.3 electron volts times electrons. Okay, this is basically close to the Dirac velocity. Okay. And this is the splitting of the gamma 1, gamma 2. So let's draw the band structure of this guy. The band structure remarkably looks like this. And this is a gamma 3 representation. These are gamma 1, gamma 2. And you can now immediately see that these conduction bands are the fermion that carries the topology. Why? We said that the topology is given by having two Dirac nodes at the zero energy. But two Dirac nodes are actually equivalent to a quadratic node. And this gamma 3 representation here, it's a degenerate twofold degeneracy that gives you a quadratic node. So this, now the topology of the model, which has to be, the model has to be topological to any bandwidth, is actually the fact that you have a conduction electron, which is a topological semi-metal enforced by a double vortex here. Now, moreover, physically, in this audience, I don't need to tell you what this resembles. This resembles the AB untwisted bilayer band structure. So in the the C electrons, the conduction electrons, are actually the electrons of an untwisted AB bilayer Bernal stacked graphene sheets. Moreover, this mass term here, this M, which is the splitting of the gamma 1 and gamma 2 representations, we know what will physically mean. Physically, this will actually be the bandwidth of the Bicester-McDonald model. This is just the splitting between the gamma 1 and gamma 2 representation here. Okay, so this parameter physically is the bandwidth of the Bicester-McDonald model. So now we built the heavy fermion, we built the conduction electron, so we have to build the coupling between them. And the model as it stands now is a localized F electron, which sits at the AA sites, a conduction electron, which sits at the AB lattice sites, and this is an AB untwisted double vortex, which carries the topology. And of course, you're going to have coupling between these two. And this coupling, you can again get it from the Bicester-McDonald model by projecting the Bicester-McDonald model into the heavy fermion band, which is V, and the conduction electron bands, which are called U here, and has a very simple form. You can actually even neglect this. This is a small, it's allowed by symmetry, but if you neglect this, it's just a constant. It's a constant between the gamma 3 representation of the heavy fermion. Remember, the heavy fermion had the gamma 3 representation at the gamma point, and the gamma 3 representation of the conduction electron. These two gamma 3 representations repel by a constant term. So now we've reached the end of the heavy fermion mapping. We have a 6x6 model of the twisted bilayer graphene. This 6x6 model looks like this. Okay. This is the heavy fermion space, Hamiltonian 0. You don't have any coupling between, well, to 0.1 electron volt error. Then I would neglect this term for now. Then you have the conduction electron, which is the AB Bernal stacked untwisted bilayer with a gap M between the gamma 1 and gamma 2 representations, and you have a coupling gamma between the gamma 3 representation of the heavy fermion and the gamma 3 representation of the conduction electron. So what happens is the following. Take this model. This is a decoupled model. Red is heavy fermion, has a gamma 3 representation here. Blue is conduction fermion, has a gamma 3 representation here. Gamma 1, gamma 2 representations are at a distance. This is 2m, or basically m, 2m. Okay. And now what happens is that this gamma term splits these two gamma 3 representations and moves them up. So this gamma term is actually the gap between the Bistrom-McDonald flat bands and the next band. And what you can ask is, how good is this model? And this is the answer to how good this model is. The red dots are the Bistrom-McDonald model. The black lines are this model. So you can see there is that, well, it does a very good job at fitting the Bistrom-McDonald model and the wave functions the same way. I haven't plotted here the overlap with the wave functions, but it's extremely good again. So now the scale.
I have a question. Yeah. So by your model, you mean this H eta K, this 6-band, what you're calling heavy fermion plus C electron model, you use that to calculate this black line band structure. Am I correct?
That's right. Okay. That's right. That's right. You use this to calculate this. That's exactly right.
Okay.
Yes.
All right, continue.
Very good.
Andrei, can I ask a question?
Yes.
So I cannot resist but think about, since you mentioned there's a Bernoulli bilayer graphene AB stack. So we know when you add a displacement field, open up a gap. So I'm curious if your model still hold in the presence of displacement field.
Yeah. So let's see. So if you add a displacement field, let's see. Does it fully open up a gap if I have, so if I have C2Z?
Yeah, supposedly for untwisted AB stack, when you add a displacement field, you open up a gap and you realize quantum valley Hall effect.
But I don't keep some see, my problem is if the electric field doesn't break C2Z times time reversal, right? So I should, maybe it should open a gap, but I should have some nodes here. So this is protected by C2ZT.
Okay, so it's probably different from Bernoulli bilayer, but the band structure is similar. Yeah. I
must be blanking out. There's an answer to your very good question, but I must be blanking out. This is certainly protected by C2Z times T. So as long as I don't break C2Z times T, and the fact that it's at zero energy is particle Hall. So this is particle Hall at zero energy, and C2ZT protects the, in other words, you cannot, it's a double vortex, so I can't get rid of it, right? Yeah, so if I have, yeah, I would have thought that if I have yeah, I have to think about it, your displacement field.
Well, I wonder if warping and those things are important in Bernoulli to open the gap, but important thing is that in your model, Andrei, an electric field would not open a gap. That's the bottom line, correct?
Yeah, an electric field will not open a gap here.
Unless the C2Z symmetry is broken somehow by hand. Okay, all right.
Right, exactly. Yes. Yeah, I have to think. I'll think about it during the break, and I'll get back to you on the electric field. I'm blanking out. I'm sorry. But that's a good point. But yeah, C2ZT here is protects this, and particle Hall keeps it at zero energy. So very good. Okay, so this, yeah, so this is the end of the heavy fermion mapping. The most important, the largest quantity in the heavy fermion mapping is this gamma, which is just the gap between the flat bands, the Bistrom-McDonald flat bands, and the next band. And after you couple the heavy fermion to the C electrons, you get exactly the band structure and exactly the topology of the flat bands of the Bistrom-McDonald model. But now you have a model where you've basically broken up your system into a heavy electron, which you can look at what interactions do, plus a conduction electron, and you have a 6x6 model. Now the Bistrom-McDonald model is an infinite shell model, of course, what you do is truncate, and truncation is very good. You can truncate to like 4 or 5 shells, but 4 or 5 shells still gives you a 50 by 50 Hamiltonian or something along that, or a 60 by 60 along that scale. So this is, this is a Hamiltonian that you can look at analytically, which is what we're going to do now. So now we go to the interactions. So the interaction Hamiltonian, what you do is you take the Coulomb interaction and you project it into these heavy electrons and conduction electrons. And you're going to have 4 terms that are important. 3 terms, very important, 1 of them less important. The most important term is going to be a density-density interaction for F electrons, which we'll find out to be the highest repulsion, and it's on-site. It's the off-site one, the nearest neighbor one is 25 times smaller or 30 times smaller than the on-site one. Then the next one that's going to be very important is going to be the density interaction between the F and C electrons, which actually will lead to a chemical potential for the C electrons in the correlated states. And the third one that's very important that leads to the Chern insulators of the correlated states is an exchange interaction between the F and C electrons. So let's see how this works. And these are the terms, the important terms. What we find is the Hubbard due of the F and F electrons is of order from calculations, the 57 or 55. Now, experimentally, this is about 30, 35. Okay, so there's depending on screening, etc. So there's, ballpark good, not obviously not exact, but certainly this is the highest energy scale computed in this problem. Now, the next,
Andrei, these numbers are based precisely on your 6-band model calculation, right?
Exactly.
So there'll be some screening by other bands, so this number can only go down a little bit from what you have. So it's
exactly.
It's consistent. Okay.
Exactly. It's based exactly. So yes, and I don't know exactly the screening length in the samples, etc. This is also this is also computed with encapsulated samples, whereas the STM that saw this that saw the value of 30 or 35 is of only one gate on one side, etc. So there's certain differences. I mean, this is on the larger side. Let's put it this way. But this is what we get computed. So all the plots will be in this number regime. Very good. Now the W's are the FC interaction, the FC density interaction, and you can see that they're actually very close to U1. And actually, there's this system is close to a very large symmetry point where if you tune some parameters, you can make these W1 and U be equal, and then you've got a huge U24 symmetry, whatever. They're not exactly equal, but this later will become a chemical potential when this density of the F electrons will acquire an expectation value. This will become a chemical potential for the C electrons. And very importantly, one that's actually a smaller value, but it's a very important parameter because it will open a gap in the correlated states, and which gap depends on this guy, is the ferromagnetic interaction between the F and C electrons. And this is a ferromagnet in a large U4 space. So it's actually a ferromagnetic coupling between U4 moments, which will be defined very soon. And the parameters are these. This is the hybridization between the F and C electrons, and the Hubbard due is what's the most important F and F interactions. So armed with this, we can now understand the correlated states. Now, I want to briefly show you some previous studies of the correlated states in the strong coupling expansion. In the strong coupling expansion, there's previous studies which basically give you a large symmetry of the model. And this symmetry is based on particle hole symmetry. So for example, with particle hole symmetry, there's a U4. If you take into account this particle hole symmetry of the McDonald model, the interacting model projected into the flat band. So this is all of these previous studies in the strong coupling were projected into flat bands, has a large symmetry U4. And then, in the chiral limit, which is some parameter taking one of the parameters, taking the A coupling of the Bistrom-McDonald model to be 0, you get to a chiral limit. This is not a particularly good limit for the experimental sample. It's a nice limit for some calculations, but the experimental sample is exactly in the opposite limit, actually. But then you have another U4 symmetry, and indeed, when you have both of these, when you take into account both of these, you have a large U4 times U4 symmetry. All these things are reproduced in the heavy fermion model, but they're reproduced without having to project. So the heavy fermion model in different limits commutes with these U4 generators, but without projection. So even when you've got the one body term, which is the kinetic term, and you don't project just to the flat bands, it still commutes with these. So for example, the limit that we're going to use is the flat limit, which is m equals 0. This m was the difference in gamma 1, gamma 2 representations here of the flat bands. Remember, the flat bands did this. This was m. When you take m to be equal to 0, you actually have a U4 symmetry in the model, and we'll be using that symmetry to characterize the states. And then make m non-zero to break the symmetry and see which state of the full U4 manifold the system will go into. This is, for example, the U4 symmetry generators. We can define them here. You don't need to. I mean, it's obviously it's a bit useless to remember them, but they can be defined, and they're a combination of orbital, valley, and spin symmetries. And the interesting thing is that this exchange term, when you write it down in terms of this U4 symmetry, is actually a U4 moment, is actually the reason why we call it an exchange term, is a ferromagnetic interaction between the U4 moments of this symmetry. So it's like a spin-spin interaction, but with a U4 moment times a U4 moment of the F electrons and of the C electrons. Okay, so armed with this, what can we do about the insulating states? And again, in the projected models, so in the strong coupling models where you just project into the flat bands, there's an understanding of these correlated states that was initially proposed by Kang and Vafek and by other authors, that basically are quantum Hall ferromagnets, or ferromagnets, they'll turn out to be Chern insulators, but ferromagnets of valley and spin. So -1 is K is valley, spin is up down, and +1 and -1 are bands, or the bands per valley per spin. So plus or minus meaning, it's a Chern number really of the bands, but I won't go into that. So you have band, spin, and valley, and you polarize them at different fillings. So at filling 1, you polarize one of these bands. At filling 2, you polarize 2 of these bands, etc., etc. And then it turns out that at filling 2, polarizing spin and valley is not the one that wins, but polarizing kind of a linear combination, which is called the intervalley coherence state, is the one that wins, etc. Okay, so these rules for the ground states at integer filling come from strong coupling.
Andrei, I have a quick question. So this energetics that you just told us about, that at some stage you want an intervalley coherent state. This is Hartree-Fock calculation result. I mean, where is this statement coming from? Because it's an energetic question, right?
Yeah. So that's a very good question. So I can say where it's coming from in the strong coupling, which is basically, in the strong coupling where you just have projection, you can solve exactly for the Hamiltonian, for an eigenstate of the Hamiltonian in some limit for the ground state for this U4 manifold, and then you do perturbation theory away from that limit.
All right, I got it now. So
but in the heavy fermion, which I'll show you, has a very simple reason actually. Okay. So I'll just show you it's coming in 2 slides. In the heavy fermion, it's got a much simpler reason.
Okay, all right.
It's very natural, actually. So that's a very good point. So I'll just, if I can take 2 slides, and then I'll come back to exactly this question, which is important. So another interesting thing about these projected models that were done in previous studies, strong coupling models, is the following: that if you now look at the excitations on top of these correlated insulator states, correlated quantum, or sometimes they're quantum hole, or Chern insulator, really, because there's no magnetic field. Sometimes they have Chern number 0, but correlated, basically ferromagnetic insulators. If you look at the excitations above them, it turns out that you can solve these exactly in strong coupling, because the ground state here, the ground states are basically Slater determinants. And you can just add an excitation, take the commutators of the Hamiltonian, solve it exactly. And what you find out is that the dispersion of the excitations on top of the strongly correlated states is very, very dispersive. You started off with a flat band, but the excitations where you ferromagnetically polarized it, but the excitations on top of it acquire a huge dispersion. And this dispersion has some characteristics, which you can see here. Is very flat at the zone boundary. It's got a gap minimum at the gamma point, okay? And it's got large dispersion of the order actually U. And moreover, it differs from different fillings. So for example, at filling 0, mu equals to 0, this is the dispersion for both electrons and holes. But at filling mu equals to 1, the dispersion for electrons is very dispersive, but dispersion for holes is not dispersive at all. So these were things that were coming out of the strong coupling approach, which could not be explained. You would just do the plot, you'd see them, you could explain them. Now I want to explain this through very intuitive, simple rules in the heavy fermion problem. All of these things can be explained. So first of all, how do you build correlated states in a fermion problem? Well, we know where the correlations are. They lie in the F electrons. And you build a trial state at your parent state, which is a state that polarizes the F electrons, but it's a Fermi surface of the C electrons. So the C electrons, you start off, the conduction electrons, you start off as just half filled, and everything that you do, your filling will be determined in the parent state by the filling of the F electrons. Okay, for example, this is at filling 0, I fill 4 F electrons, I can fill 8 F electrons, I fill 4 F electrons per unit cell. For example, this is F electrons spin up, valley plus, and px plus ipy. This is 1, right? There's px plus ipy and px minus ipy F electrons. This is the px minus ipy F electron. You fill them, and you fill them based, actually, what we find is that you have to fill them based on a Hund's rule. So it's very simple. It's Hund's rule. You just make the most symmetric U4 representation. This is basically a U4 Hund's rule. You just, because these are U4 multiplets. And when m equals to 0, as I said, there's a U4 symmetry, so I can rotate this state into any other manifold. For example, this is the KIVC state. This is the KIVC state. It's just a rotation of the fully of this state valley polarized. You can see that everything here is in valley plus, okay? And valley in one valley, it's the rotation of the very polarized state, a U4 rotation, the KIVC state. And this is energetically the same when m equals to 0, but it will get different energy when m is not 0 and m is 3.7 electron volts in the Bistrom-McDonald model. So let's see how this goes. So you start off with this parent state, and now you do Hartree-Fock. But it turns out that you only need to do one-shot Hartree-Fock in this model in order to actually get the physics. You can see that the one-shot Hartree-Fock and the self-consistent Hartree-Fock on the heavy fermion model basically gives you a very similar band structure. Okay, so the one-shot Hartree-Fock, fortunately, can be done analytically. So you take that wave function, the parent wave function, you compute the expectation value of the density operators of the F electrons, and then you feed them into the model to build a one-shot Hartree-Fock and to obtain the band structure. And you can sort of understand immediately what happens. We knew that you had a conduction electron, okay? This conduction electron would gap with the hybridization term. The hybridization term would be sorry, excuse me. After the hybridization term, the band structure looked like this, okay, just like the Bistrom-McDonald band structure of these. And then you had these flat bands, but now these flat bands are polarized by Hubbard U. So I'm going to move the flat bands here, which is what this does. Okay, here. So the flat bands have moved because of the parent state, because of the ferromagnetism. And now the flat bands cross the dispersive band. Once it crosses the dispersive band, they have level repulsion. And this is the reason why you get these splittings here. These are just level repulsions here. And now you can understand immediately the excitation spectrum on top of the insulating states that I showed you before. The excitation spectrum on top of the insulating states, I told you that it has a minimum at the gamma point. This is clearly the reason for that is that the conduction electron had a minimum at the gamma point. I told you that it's quite flat at the zone boundary. The reason is at the zone boundary, it's just the F fermion, which is also flat, and it's got a large bandwidth. And this is also obvious because the bandwidth is basically controlled by U, right? I move the fermion up, it's controlled by U minus gamma, which is gamma is the gap of the Bistritzer-McDonald spectrum, which is still very large. So all these things that you could see in strong coupling are now explained. So this is at mu equals to 0. Now what you can do is actually gain an analytic understanding of this in one shot Hartree-Fock. And this analytic understanding is very simple. All that you need to do is look at the gamma point and look at the sector between the gamma 1 and gamma 2 representations of the Hartree-Fock bands. And this sector, remember, had in the single particle only m times sigma x, this single particle term. But now in Hartree-Fock, it acquires this term, which is the U4 spin ferromagnetic interaction. And this O is the mean field of the F fermion. This OF just comes out of taking the parent states, which is polarized, whatever, and computing C dagger or F dagger F. Okay. And now I come back to Shankar's question about the difference between states. Now you can see immediately which state will win. Why? It's a very simple argument. Now you only need to look at this term and see which gap will be maximal. Okay, so for valley polarized state, this term is m sigma x, and if I compute the Hartree-Fock term, I will get j times tau z. So I get two terms that commute. Okay, this m sigma x commutes to tau is in valley space, sigma is in orbital space, they commute. Now, if I do the KAVC, now the situation changes, is m sigma x minus j sigma y. So these terms anti-commute. Because they anti-commute, this opens a larger gap. And this state wins at m not equal to, at any m not equal to 0. They're, of course, identical. They have the same gap and the same energy at m is equal to 0. But the KAVC wins at m equals 0. And the reason is that the order parameter that's formed by the direct ferromagnetic interaction between the F and C electrons anti-commutes with a single particle term, whereas it commutes for the valley polarized state. So then you have these simple rules for the
Andrei, may I ask a quick question? I did not follow everything totally, but it seems that there is a constraint on the validity of the theory, right? J must be larger than 2m or something like that, right?
That's right, and it is. So that's right. So, and it is, these are the values. So m is 2m is 7, j is 16. No,
theoretically, I think it's absolutely fine. But as you said, your U1 is not quite what the experiment sees. So there may still be a question. You see what I'm saying? I mean, theoretically, it's completely consistent. I totally accept it.
But gamma is also not what the experiment sees. So somehow they're all like reduced, right?
Okay. So, no, I buy the theory, but I'm just saying is that if I want to be a complete, like, I do not want to accept anything, you need J to be larger than 2m. Now, what you're telling me within the model, you do find J to be larger than 2m. That's good. But if experimentally J is not larger than 2m, we have a problem. That's all I'm saying.
Right. But I agree. But yeah, I agree. But I think experimentally what happens is that all these numbers basically scale down somehow.
I see. I understand what you're saying. Okay, I see. What you're saying is that they do not relatively shift. It's just that everything you have you got somehow the lower bound. I mean, your number is the largest possible. Okay, I got it.
Certainly that's true for U and gamma. Now I don't know how to compute. I don't know experimentally how to get J. You know, like U can be obtained by just doing some density by just but and gamma can be obtained by also by STM, I guess, right, by going to the excited bands where you don't have much Coulomb and then tunneling and seeing the difference. So those ones are scaled down. Those ones are basically half of what we're saying here, or both of them. So yes, I would imagine that they, I mean, it's a valid point. I don't know. I would hope that they scale down. Certainly it's true that gamma and U scale down. Now the other ones, maybe it's it's a hope that the other ones
please continue. I just wanted to make sure I'm understanding.
Are scaled down too, mentally. Yeah. So, but with these caveats, there's now two simple rules. There's a Hund's rule for the F electrons, which just basically gives the correlated states, and then in this large U4 manifold on which this Hund's rule is, then you get to the actual state by maximizing the gap given by just this simple combination of the single particle gap of the gamma 1 and gamma 2 states and the exchange between the F and C electrons, which basically becomes a gap in the C electrons given by the expectation value of the order parameter of the F electrons. Okay, so with that, basically, I'm going to take, because I've already took too much, I'm going to take just 3 more minutes to explain 2 more things. So remember, I was saying that in the previous slide that at mu equals 1, there is now a difference between mu equals 1 is particle Hall related to mu equals -1. So at mu equals 1, there's no need for the excitations on top of the insulating state to be particle Hall symmetric around mu equals 1. They have to look the same at mu equals -1. But so far, the electron excitations on top of the mu equals 1 state are much more dispersive than the Hall excitations in strong coupling. But actually, this is immediately, and this was not understood in that calculation, this is immediately understood in heavy fermion. Why? At mu equals to 0, we had these electrons, the F electrons moving up at U, okay? But now at mu equals to, here, instead of putting 1, I put -1, so electrons will become holes, and vice versa. Instead of putting this, you remember we had a term which was W rho F rho C in our heavy fermion model. And this now acts as a chemical potential to the C electrons, and the C electrons, they have a shift. And because W was the same value as U, then the shift shifts the F electrons exactly at the bottom of the band, or close to the bottom of the band of the C electrons. So then when you introduce couplings, there's not much that they can couple with, and the band remains kind of flat. And this was this band. Again, as I said, just to confuse people, I've now put this is -1, this is -1, this is 1, and this band, the dispersive one, was this band. So we understand also why there's this massive particle Hall asymmetry at non-zero filling. This particle Hall asymmetry in non-zero filling can be seen in these compressibility measurements. Okay, so with that, I wanted to close, but before I close, I also want to tell you that there's simple understanding of how to obtain this Chern number. So some of these states at different fillings have Chern numbers. Now, these correlated states. Now, these Chern numbers are actually just the opening of the gap of this quadratic fermion, and depending on how you open it in different values, you can obviously lead to Chern numbers. It can obviously lead to Chern numbers. And there's a consistency between the strong coupling and the heavy fermion calculation, which gives you the same description. Now, the last thing that I wanted to tell you is the local moments. So we want to claim, although we don't have a calculation yet, that potentially this type of heavy fermion physics can also give you the Pomeranchuk instabilities and the superconductivity. The Pomeranchuk instabilities would basically come also because, you know, the coupling between heavy fermions, for example, at mu equals 1 or -1, where they see this most strongly, there's a minimal coupling just because the heavy fermion is actually very close to the bottom of the band, and it doesn't hybridize very much because to the bottom of the zero density point of the conduction band, it doesn't hybridize very much because there's not much density of states there, except for a small, very small region where it's quadratic. You can see that this region is very small. So then you have these loosely coupled moments, these loosely coupled F electron moments, which one could claim are responsible for the Pomeranchuk effect. The next thing is superconductivity, which in strong coupling in the projected models, you just cannot get. So if you take superconductivity in a projected model, these projected models where you just project the Coulomb interaction into this flat band and there's no kinetic turn, you can actually prove that the two-particle continuum, the two-particle spectrum has no bound state below the continuum. So there's nothing like the Cooper pair. You can prove that basically Kohn-Luttinger's theorem does not work for projected Hamiltonians. You need kinetic energy. So this heavy fermion model now has kinetic energy. So hopefully the hope is that we can get superconductivity. But so far, these are just hopes, and more calculations are necessary. So I took already too long of your time. So I thank you for your attention.
Thank you very much, Andrei.
Thank you.
Yeah. Hey, Jiabin, I want to ask a question first because I have to run. I'm going to talk to Andrei at
Yeah,
one.
sure, please.
One question I want to ask right now. So, Andrei, this is very nice. I did not know about this work, and I buy quite a bit of it. I have to think a little bit. But my question is a physical question. So, in regular heavy fermions, we kind of know where meaning just from simple chemistry, we know there is, you know, it's a compound, there is a very heavy metal like uranium or something, that from the local moments, because that's like almost atomic, and then there's something else that gives me the conduction electrons, and it's kind of like very physical, even before you do any theory, right? Yeah. But here, can you give a simple picture where it's arising from? I followed the algebra completely, but where is it coming from? It's just all carbon, right? All carbon here, right? So is there a...
Yeah, exactly. So it's clearly a different mechanism.
Yes.
But it's clearly a different mechanism, but I would argue that it has, that basically for any models that have this flat band and a small gap, it will have to be this way. So here's so this is very good point. And here's my general argument. I would say, so imagine that I have a model that looks like this, okay? Like the Bistritzer-McDonald model. I'm not going to draw it. Of course, there's two bands here, okay? But imagine we have a model that looks like this, right? This model, here, there cannot be any Berry phase, right? Because it's far away from any bands, okay? It's far away from any of these other bands here. And, you know, it's likely, okay, I mean, maybe there was some level crossing at some point, and then the band gap at this K point becomes large, but likely not. So here I cannot have Berry phases because I have a huge gap to other bands, right? So, by the way, this is the Bistritzer-McDonald model, because this velocity here of this guy is actually this very close to is 9/10 of the Dirac velocity in graphene of these bands, right? So I claim that these bands, so if there's no Berry phase here, then I can always represent these as localized orbitals, at least a large portion of these bands. Since I don't have any Berry phase, like it's just localized orbitals. So I claim that number one, I have the localized orbitals, but number two, because there's a small gap here, okay, this is where the Berry phase, if there's any, and there will be, because it's right, there's just three levels. It's basically you're gonna get Berry phases around, right, and around any 3-level or 2-level system, 3-level, 4-level system, you're gonna get. Here's where the Berry phases are, and this guy will have to have some conduction electrons or some delocalized electrons, just because, you know, its overlap with the localized moments has to be small, because you've got a lot of Berry phases and a lot of mixing of bands. So I would claim that this topological So heavy fermion coupled to some topological semi-metal, which gives you the Berry phases, is actually very generic, or could be very generic for band structures that look
You
like
answered
this.
my question. You answered my question.
Does that make sense?
Yeah, it makes sense. So my advice to you would be, I mean, you don't need more fame. Maybe you need more money, but you don't need more fame. So I would say that you should emphasize this topological aspect, because saying it's heavy fermion, there's a whole mafia out there, heavy fermion, you know, but your mechanism is very different. Topology is the main thing here. You know, topology generates the heavy fermion physics. It's not like it's heavy fermion intrinsically. You are doing
it's not.
But I'm saying you are doing a heavy fermion community a favor by calling it heavy fermion. It's a totally different mechanism. Then in the end, Hamiltonian has this itinerant versus localized electron coupling, but it's coming from topology, as you explained right now.
That's right. But I'm hoping that these heavy fermion people, they've done a lot, right? And so in the sense of like having a lot of machinery. So I'm hoping that the heavy fermion people can get involved and figure out some things that at least I cannot. Right?
I see. Okay.
Because I don't know. But so that's also part of like the calling it. By the way.
Good point. This we may get some theories with new tools coming in. All right, I gotta go.
Right, exactly.
Yeah, I'm going to see you at 1:30 on Zoom again. Okay.
Yes.
All right.
See you soon. Thanks. Bye.
I see you one hands up. Yajin, please.
Hi, Andrei. Thank you for a very nice talk. I have two short questions. The first question is, so in heavy fermion, we know this condo insulator or like this. So can I actually think the B-Street by McDonald model as a consequence of this spin hybridized with the electron? And that's the first question. And the second question is, can you comment on spin valley lock? What I mean is those state people reported theoretically with a K value with spin up and a K prime value with spin down. And I don't think I see those state in your.
Sorry, yeah. So let me. So which state do you want me to comment?
I don't see the spin valley lock. Do you have a spin valley lock state? That's probably my question.
A spin valley.
No,
I couldn't
so
hear it.
It's similar to those TND, like a niobium dicyanide, but there are some theory arguing that such a state can also happen from graphene due to those anti-ferro-Hans rule interaction. That's very interesting, but I'm curious, can you also get that?
So I have all the states. I'm not. I'm not familiar with the state. So that's
so
you know.
It's basically K with a spin up and K prime with spin down. So
yeah, I mean, K with spin up and K like this. These are the two valleys. So it's.
Yeah, it's two valleys.
Valley plus with spin up, valley minus with spin down, or what?
That's correct.
So this is at filling. This is at filling 2.
Yes,
or minus 2.
It has been proposed. Maybe this would be the ground state of -2. No more state of the nucleus -2.
Yeah, I'm not. I mean, I would have to check it. This is a U. So at 2, you can get. You can get the state that's most symmetric under exchange. So I can get F1 plus up, F2 plus up, for example, and then rotate it. Okay, and I would have to check if this is part of the U4 manifold. I mean, I don't see why it wouldn't be, but I'm not right. So basically, there's a U4 manifold, and this is quite large. So I can't see it. I can't see it by eye if it's part of that manifold, But I can tell you, I can tell you in like 30 minutes if this is. I would have to just check if it's part of this. If it's part of this manifold, right?
Okay. Yeah. So going back to the first question, I just want to confirm. So should I actually, based on your theory, I should really think of the B-Street-McDonald band structure as a consequence of those spin coupled to electron? If I use the heavy fermion language, is that the right way to think about it?
So at the magic angle, I think you certainly get, I'm not sure if you can go the other way. Certainly at the magic angle, what you say is true, right? You get, local moments, and then you get some conduction electrons, and then at some fillings, they're loosely coupled. Okay, so this is where it's similar to quantum physics, as you say. So but this is only at some filling around. So this is at filling 1 or -1. Okay, so at other fillings they're strongly coupled. Okay, so I wouldn't say that the Bicester-McDonald model is a consequence of this. I would say that this is a consequence of the Bicester-McDonald model, but it might be, so far it's not clear that you can have one without the other. Okay. But the way I'm looking at it now is that this is a consequence of the Bicester-McDonald model, and of having, it's really a consequence of having, just as we spoke with Shankar, having this type of band structure is really a consequence of flat bands, unless they're Landau levels, or unless Landau levels have this, right? So it's not, you don't have a minimum. Flat bands, unless unless they don't have a minimum around somewhere, flat bands can always have some heavy fermion part, because the part that's far away from everything else is going to be localized. So then, and they're going to have some conduction electron part, where so I claim that you can always write down this type of model. Now, how good this model is, meaning how localized the electrons are, and how similar to quantum physics, how loosely coupled these things are, that depends on the actual parameters. But so how efficient is this model in determining the physics depends on the actual parameters. But you can always write down such a model, I think. But in the Bicester-McDonald model at the magic angle, this is a particularly good description, and there's different fillings at which you can get what you said, similar to quantum physics, local moments loosely coupled to some conduction band, but not at all fillings. So at filling 0, for example, you have, where is it? Sorry, at filling 0, you have the heavy fermion coupled to some high density of states. So you're going to get a lot of, you're going to get at filling 0, you're going to get, you're not going to get loosely coupled moments anymore, because these large Fermi surface actually couples these loosely coupled moments. Does it make sense?
Oh yeah, sorry, I just got offline for some minutes, but yeah, I think okay.
Okay.
Yeah, Ming, please.
Can you hear me? Okay. Yeah, so I have two questions. So you showed us the how the intervallic coherent state emerge in the neutral filling factors. Does the same picture work in -2 or +2? You have larger condensation energy.
Yes, exactly. Exactly. It's the same. Yeah, very good. Thanks for that. So yeah, it's just maximizing this gap here.
Okay.
It's larger. You can understand everything just from looking at the gamma point. Right. This is the gap at the gamma point of the heavy fermion model with polarized F electrons. This is the result after one shot Hartree-Fock. So you take this correlated ground state, which is where just the F electrons give you the filling. The F electrons are the ones that control the filling. The Fermi surface in the C electron is this, and then you just compute it. You compute the expectation value of the order parameter of the F electrons, and you introduce this in Hartree-Fock into the model. It gives you this model at the gamma point. So you could, the heavy fermion model had some K here, right? But at the gamma point, this is 0. So it just gives you this model. This is the U of the F electrons, and this is the way it interacts with the C electrons. Is just this J, and it's just a question of whether J commutes with M or not.
Okay, do you get like extra self energy by in the valley polarized state because you have two completely like empty flavors, right?
So
maybe, yeah.
So if you mean okay, so if we compute, so this is the analytic result, right? Because
okay,
but you can actually compute the self-consistent Hartree-Fock and check this, right? So it's not just like we said that the gamma, this is the simplest, this is the simple result, right? That the gamma equals to 0 point gives you the gap at gamma equals to 0 gives you the which state it is. We actually check this, that if you just take the entire Hartree-Fock and do the self-consistent one and sum its energies, then it gives you the same result as just taking this simple k equals to 0 gap.
Okay, 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 I get it. Yeah. Yeah, that makes sense. And another question is the general comments you made about superconductivity. Are you indicating that if you include the remote dispersive band, you can get like Cooper instability instead of just stay in the two-band manifold? Is that what you're saying?
Well, so what I'm saying is that you have to add kinetic energy. So you can either add kinetic energy of the low-lying bands, right? So what I'm saying is that the just projected Hamiltonian into the if you take the Coulomb Hamiltonian and project it into the lowest lying bands, into that will not have superconductivity. That does not have. You can prove that there's no bound state.
I see. Okay. I see.
Now that, because it's projected, it has 0 kinetic energy. So you need to add kinetic energy. Now what you can do is add kinetic energy in the strong coupling model, which involves projecting the interaction into these bands and then adding kinetic energy to these flat bands. Then this theorem doesn't apply. Okay. And you possibly could get superconductivity, right? Even with this large Hubbard. I mean, there's all these theories of superconductivity, but what I'm saying is that this is not easy to solve, because now you've projected and you add kinetic energy, and all your symmetries, these U4 symmetries, etc., are gone. Whereas in the heavy fermion model, the symmetries still stay there even with the dispersion. So the heavy fermion model is actually, and you've got this separation of scales. So for example, I would know, okay, so for example, in the heavy fermion model, I would know that if I have an order parameter that's got large amplitude where the heavy fermions are, and that's on site, then that's not going to be competitive because there's a huge Hubbard U there. Right. So the separation of scales is what makes this I think useful, right? So I know that, for example, anything in the heavy fermion model, anything that's got any order parameter that's got amplitudes anywhere here, on-site amplitude anywhere here, is not going to be good, because that's got a huge Hubbard U, right? So those are kind of the rules of There's a huge Hubbard U, so I still don't know how to fully get superconductivity in this model. I mean, I know there's many models, and written by many people. I've written one model too, but I don't. I think the problem is not. I think it's not fully solved.
Yeah, I agree.
Yeah.
Okay. Thank you.
Thank you.
Okay. Any other questions? If not, let us thank Andrei again for the wonderful talk.
Thank you.
Thank you. And